Okay, so now we're looking at again we're trying to prove this proposition that it seems that our problem is boiling down to this. If it appears that if we can prove that for a group that is not cyclic, if we can prove that the order of the group, and if let's say a group is not cyclic and the order of the group is p to the alpha times m, where p and m are relatively prime, then it appears that if we can show that this statement here, G is not cyclic, order of G is p to the alpha times m, it appears that if we can prove that, if we can prove that, this statement implies that there is some element whose order equals to p to the alpha times L, where L is a divisor of m. Okay, so that's a mouthful. Well, let's call all this set of claims A. Okay, that G is not cyclic and order of G equals to p to the alpha times m, and GCD of p and m equals to 1. Let's call that A. If you can show that big A, calling it big A implies that there is some little g in G whose order is p to the alpha times L, right? That appears to be enough to actually prove the entire theorem, because we've already proved that if G is cyclic, well, we're guaranteed a subgroup of order p to the alpha. And now it's, if G is not cyclic, right, then it appears that if we can show that order of G is of the form p to the alpha times L, well, that seems to be sufficient. But again, the main challenge is, how do we prove that there's an element in the group whose order is p to the alpha times L, right? So given the conditions here, the group is not cyclic, p and m are relatively prime. So again, one thing we're noticing is that if p and m are relatively prime, we're just drawing the conclusions, the consequences. And one of the things we realized was that, look, if m is in, right, so we're saying before that, well, p and m are relatively prime. So what does that mean? Doesn't it mean that for every divisor L of m, that element is in Z mod PZ star, right? The group of all elements. Ooh, is that even true? Jeez. Well, sure it is, but it's gonna be mod P, yeah? Okay. So L is gonna be every element of M, every divisor of M is gonna be an element of Z mod PZ star, right? Of course, uh, considered mod P. But once again, it's unclear how that guarantees us that we have an element of the group whose order is p to the alpha times L. Well, it's hard to say. Oh, maybe, huh. Oh, do we have a formula for how many divisors there are for a given element? I mean, there's a formula in number theory, but will that really be helpful to us? Well, unless we know the number's prime factorization. Because one bizarre strategy appears to say the following. Well, watch. For all G element of G, right? For every element of the group G, we know the following, that, well, well, does Lagrange's theorem tell us that the order of every element of the group must divide the order of the group? So for all G, order of G must divide p to the alpha times L, right? So maybe if we can do the following, suppose we're able to find all the possible divisors, right? So aren't we saying that the possible orders for elements, right? Let's say we are to count all the possible orders of elements. So can we say this, that think about, let's then consider this set, the set of all p to the I times L, such that L divides M and I is less than or equal great is at least 0 and at most alpha, right? This set here, how many elements does it have, right? So let's call this set should we give let's just call it what? A. Oh, B. Okay, fine. The set B. This is going to be the set of all possible orders of elements in G. That is, if all the possible orders of elements of G were to appear, well, how many elements are in B is the question. So the idea is maybe if you can count the number of elements in B, right, if you can count the order of B, all the possible orders that can happen for a group, for a given group G, and maybe compare that to what? Um, yeah, compare that to what? Wait, this idea is bizarre. Yeah, completely lost it. There was something here, but it appears we've just lost it. Okay, well, we have a set, and this set counts all the possible. Right. So if we have, let's say, a group of orders 8, okay. If you have a group of order, yeah, sure. Let's say, sure. Why not 8? If you have a group of order 8, right? If order of some group K, if the order of some group K is 8, then Lagrange's theorem tells us that the order of every subgroup H of K must be such that the order of H divides K, right? Divides the order of K. All right. So what does that tell us? It tells us that if we were to list down the possible orders of subgroups or elements, well, we could have a subgroup of order 1, subgroup of order 2, subgroup of order 2 squared, subgroup of order 2 cubed. These appear to be the only, isn't this the list of all the possible divisors of 8? Okay, question, well, is it necessarily true that every divisor of the group corresponds to a subgroup? That is, if let's say 2 squared divides 8, there must be a subgroup of order 2 squared. So that would be the converse of Lagrange's theorem, and so at least we are not sure, uh, we're not sure if it's true or not. Lagrange's theorem is true that the order of every subgroup must divide the order of the group, but whether it is true that the order of every, that if you have a divisor of the group, then you must have a subgroup, that's unclear. So yeah, so we're not guaranteed that, but here's what we know for sure is that if all the possible subgroups were exhausted, right? If, like, we know that every subgroup, if there is a subgroup of K, it's gonna have either order 1, 2, 2 squared, or 2 cubed. We're not sure if 1 will be taken by some subgroup 2, 2 squared, and 2 cubed. But we know that if the most, the possible orders, all the possible, if we're to count the possible orders of subgroups, well, this is an exhaustive list of them. That is, if we were to come up with, if we were to look at a list B, which we're going to label as following, B is going to be the set of all order of K such that, let's say order of, let's just pick an element, let's say order of X, such that X is in, sorry, such that order of X such that order of X divides order of K. Oh, no, Jesus. Alright, we just invoked Jesus there. Okay, so let's say this. The set of all X such that order of the set of all order of x such that x is a subgroup of B, well, at least in the case when, in this case, sorry, subgroup of K, right? So subgroup of K, the set of all x, order of x, such that x is a subgroup of K. Well, if K is if the order of K turn is 8, we're saying that this, whatever this set is, it's gonna be a subset of the set 1, 2, 2 squared, 2 cubed, is the idea, right? See if that makes sense to you. That is, if you consider the set of all, if you consider the set of all orders of subgroups, it's going to be a subset of the set of containing every divisor of the order of the group itself. Okay. So if we ask about, well, what's the order of B, that will be right. So let's see if that makes sense to you, right? So actually we're not going to call this B, but we're going to call this set B instead. The set of all possible orders, we're going to call that B. Okay. So now back to our problem here. Well, we're not sure if this is going to help us, but if we have some group whose order is p to the alpha times m, right? If you have some group whose order is p to the alpha times m, right? Then we can ask the same question. Well, what's the set of all possible orders of subgroups of G, right? Let's call that set B, the set of all possible orders of subgroups of G, and that set is just going to be, well, can we call it p to the I times L, right? Such that, again, well, such a what? Such that, well, I is less than or equal to alpha, at least 0 at most alpha, and L divides M, right? This list here, right? And in particular, we can talk about the order of it. That is, what is the size? How many elements are there in the set of all possible orders of subgroups of G, right? And again, why was this brought up? There was an idea, but not sure if we can. It just came and then went, right? And it appears to be the sort of thing that may resolve this dilemma for us. How can we use this information? Well, we want to say that there is an element of the group. There's an element little g in the group such that the order of G equals to p to the alpha times L, right? That is, the power of p to the alpha remains the same, but we're getting some L. That is, we have a subgroup that has p to the alpha times some divisor of m. How can we guarantee that this is true? Well, let's try contradiction. Okay, so suppose the statement is not true, right? Suppose there does not exist, right, a little g element of G such that order of little g equals to p to the alpha times L, right? Sorry. Right. So there is no subgroup which is of the form p to the alpha times L. What does that mean? Doesn't that mean that then for all little g in G, order of G equals to p to the I, let's say p to the j times L, where j is strictly less than alpha and at least 0. Okay. So one approach is to contradict this statement. That is to say that if the group is actually not cyclic, this can't happen. That is, they can't, all subgroups can't be of the form p to the j times l where j is less than alpha. There's going to be at least one whose order is p to the alpha times some divisor of m, right? So again, so this is what I would want to contradict this statement here, contradict it somehow. At the moment, as yet, it's unclear what would we contradict here. Well, one is maybe show that if for all g and g, order of g equals to p to the j times l, where j is less than alpha, perhaps we can say that, well, that leads us to the conclusion that the group is cyclic, or that p and l are not relatively prime. That's another possible contradiction. Or that actually there is some element of order p to the alpha times l, right? Right, so what to contradict? Well, one way to proceed here is to just follow the consequences. Okay, suppose that for all g and g, order of g equals to p to the j times l. Okay, and j is always less than alpha. Well, what does that mean? Hmm. Well, yeah, it's again unclear how to proceed from here. But again, it's also not clear that we should abandon this approach. It may or may not be promising. um, so there was this idea about counting. Suppose we count, then if we assume that, well, for all g order of g equals p to the j times l, suppose we count, well, what is the maximum, what is the, in that case, given that the power of p must always be less than alpha, in that case, what is, how large is the set of all possible cardinalities of subgroups going to be? Right? The set of all possible orders of subgroups going to be kind of similar to the set here B, which was, if we consider all the possible divisors of the order of the group, well, what's the cardinality of that set? The cardinality of the set of all possible divisors of the group. That would give us the cardinality of the set of all possible cardinalities of subgroups of the group. Okay, well, can we do the same here? Well, what is the cardinality of the set of all possible divisors? So the set of all possible orders of elements here, right? So if all of them always have a power, p to the j is always less than uh, j is always less than alpha, right? So, and let's say we actually calculated this and got a number, right? So that is, let's call this set B, or let's call it C. All right. So Right, so we just run out of time. Again, it's unclear whether this approach will help us or not, but again, we don't want to abandon an approach without having a good reason to abandon it, right? Because it may be that we're just not pushing hard enough. So let's see. So next time it appears, either we'll come up with a breakthrough and see why make this approach work, or we'll figure out at least why it doesn't work, which will now give us the liberty to try something else. Thank you once again for watching this video, and have a relentless week. Bye.